morning everyone, I am Nitish. I am doing my PhD at UC San Diego, working with Professor Robert Heath, and I will present my work today on frequency-reconfigurable ad hoc networks with dynamic metasurface antennas. This work is in collaboration with my colleagues Kilinc and Carlson from UC San Diego. I will start by discussing the motivation and background for this work. To begin with, I will discuss some background on multiple antenna ad hoc networks. So in this work, we assume an ad hoc network where there are multiple transmitter-receiver pairs which operate simultaneously on the same frequency resource. So as these pairs operate simultaneously on the same frequency resource, there is the problem of interference. And we are focusing on a single hop network where there is single link between TX and RX. So to cancel interference at the receiver, one solution is to use multiple antennas, and we are focusing on multiple antenna ad hoc networks. So in this architecture, we assume that there are multiple antennas, and each antenna has one receive RF chain accompanied by ADC and DSP. So a well-known fact in ad hoc network literature is that as the number of antennas on the receiver scales, there is more capability of cancelling interferers. So number of antennas increase the chances of cancelling more number of interferers. But this comes with a bottleneck. The bottleneck is that as you scale the number of antennas in a fully digital receiver, the power consumption and the hardware cost also increases. So the question is there any other energy efficient alternative to a fully digital receiver that is suitable for scaling up ad hoc networks? So in our group, we are focusing on this new kind of antenna architecture called as dynamic metasurface antenna, and we explore the use of DMA for ad hoc networks. Let me start by discussing what is a DMA. So a DMA is a frequency-reconfigurable antenna which has this leaky waveguide structure. So you pass signal from one end through a waveguide, and on top of this waveguide we have multiple slots that radiate out power. So to give a simple analogy, you must have used a garden hose where we put water from one end and then it sprinkles water. So similar to a garden hose, we can tune the radiation through these radiation reconfigurable slots. So in a garden hose, we have these multiple knobs where you can change the water flow level. So similar to that, here the way this operates is we can change the electrical length of these slots by tuning the resonant frequency through some low-powered electronics like varactor diodes or PIN diodes, which is controlled through this DMA controller. The second benefit is that adding more slots on the DMA does not lead to any significant additional power overhead. So we want to use these benefits of a DMA to make ad hoc networks more energy efficient. I will discuss some prior work on this topic. So there has been a lot of foundational work on modeling DMAs in David Smith's group in Duke University, and these references did some initial theoretical modeling where they modeled these reconfigurable slots as discrete dipoles and also verified through hardware proof of concept. Once this idea gained traction in the wireless community, there has been a lot of work on integrating DMAs in cellular systems. There has been work on both uplink and downlink integration of DMAs. And our group has been recently focusing on integrating DMAs in a tri-hybrid MIMO network where we have digital precoding, analog precoding, and reconfigurable antenna paradigm with this DMA metasurfaces. Specifically, I will focus on this prior work which we presented recently at the ICC conference, where we focused on frequency selective beamforming with DMAs. So in this, we have explored a new paradigm where the DMA can be used to operate at different frequency bands, and it can dynamically switch between the carrier frequency. The benefit of this is that we have observed there is some coupling between the dominant beam angle and the operating frequency. So similar to a frequency hopping technique that we have seen in the CDMA technology, this paradigm helps us to configure the operating frequency and the resonant frequency of the DMA optimally for each beamforming angle. So the goal in this talk is to explore this frequency selective beamforming paradigm for ad hoc networks. So in our proposal, we are proposing frequency-reconfigurable ad hoc networks with dynamic metasurface antennas. So here in an ad hoc network, there are multiple TX-RX pairs, and for each receiver, there are multiple interfering transmitters as well, and we want to cancel out those interfering transmitters by dynamically changing the operating frequency of the DMA through this low power electronics. So I will discuss some assumptions for the network model. We are assuming that each receiver has a DMA with multiple radiating slots, and each transmitter has single antenna. There are multiple TX-RX pairs which operate at different frequencies in a given feasible range. So the feasible range here is from 13.6 GHz to 16.4 GHz. And within this huge spectrum, we allocate different smaller bands of bandwidth B. So there are K overlapping, non-overlapping bands, each of bandwidth B within this tuning range. And the assumption is that this bandwidth B is small compared to the operating frequency. So each communication link is narrowband. With this approach, the set of interferers for each RX depends on the frequency assignment for each pair in the ad hoc network. So I will discuss how we allocate the frequency in the upcoming slide. The benefit of this is that if we fix the density of the ad hoc network, then for each RX, the average number of interferers reduces because we are dynamically allocating the operating frequency band. So the goal of this research talk is to investigate the performance trends of the DMA for different parameter settings like the tuning bandwidth and the number of slots. Let's look at the system model. So in the system model, we have multiple transmitters which transmit to the respective receiver, and we have this desired transmitter which transmits at frequency FT, that's the operating frequency. And there are other transmitters which also transmit at the same frequency, that's why they interfere with this receiver. So the signal component is H0 times X0. X0 is the transmit symbol. And there are n int number of interferers which also transmit on the same frequency. And then we have the noise vector impinging on these slots on the DMA. Now the DMA applies a combining vector which is denoted by WDMA. So this WDMA is a combining vector that is obtained by the resonant frequency control. An additional effect in the DMA is that as the signal propagates within this waveguide, there is an intrinsic DMA channel which has some phase and magnitude change at each slot. So effectively, we get this effective signal, which is element plus product of the wireless reset signal and then the intrinsic DMA channel. And the DMA applies a combining vector, WDMA, to get a scalar received signal. So you can write different components of the received signal in terms of the combining vector, which applies on the signal component as well as the interfering and noise component. Let's look at some aspects of what this combining vector is made up of. So, as I discussed earlier, the DMA operates by resonant frequency control. So each slot on this DMA has this resonant frequency which can be tuned dynamically through the low power elements like corrector diodes or PIN diodes. So the main objective is to configure the resonant frequency for each slot. Now each slot can be modeled as a magnetic dipole, and the magnetic dipole is governed through this variable called as magnetic polarizability, which is given by this Lorentzian expression. So our goal is to configure the resonant frequency which changes the polarizability that impacts the beamforming weight. Now let's look at what this is a complex number, and let's look at the locus of this complex number in the complex domain. So in a typical phased array, we have unit modulus constraint, which means in a phased array for the magnitude is uniform across different phases. Whereas here we see that the locus of the DMA beamforming weight is a circle offset from the origin. So it has a coupled magnitude and phase constraint. So that's the key challenge with the DMA, because it's a non-trivial problem to optimize a DMA because of this coupled magnitude phase constraint, which can also be observed in this plot, in this magnitude and phase plot. So as we said, the resonant frequency, the magnitude and phase curve shift depending on the resonant frequency. So I will discuss how to configure the DMA operating frequency and resonant frequency to obtain a good SINR for the receiver. So this is the signal to interference and noise ratio, where we have this received signal power which depends on the combining vector. Now the first step is to configure the operating frequency. For this we only focus on the received signal power term, and we obtain the operating frequency by maximizing this term, which is one component of the received signal power. So you can check out the simplification in this paper, reference 1, which is our previous work in ICC. This is a simple optimization because it's just a scalar numerical search over the feasible range. So by doing this, we obtain the operating frequency to maximize the received signal power. Now once we have the operating frequency, we move to configure the resonant frequency of each slot on the DMA. So to do that, we have this SINR objective, which has the resonant frequency dependence through the combining vector. For optimizing the resonant frequency, we adopt the gradient ascent update rule. We initialize all the resonant frequencies same as the operating frequency from step 1. And in the reference 1, we have showed that this assignment is actually optimal for a line of sight channel. And here we are dealing with a more configured objective function where we have several interfering channels. So that's why we have to use a numerical method to configure the resonant frequency. So we adopt this gradient ascent update rule where we iterate over different iterations to update the resonant frequency based on the partial derivative of the SINR with respect to the resonant frequency. So once we configure both operating frequency and resonant frequency, we have the optimal SINR for each TXRX pair. Then we perform numerical simulations for adhoc network. In the simulations, we adopt a ray tracing environment in the Siona software where we have this Manhattan grid, and this grid has multiple TXRX pairs. To simulate the TXRX pairs, we use a Poisson point process, where the number of TXRX pairs is a Poisson random variable governed by the density lambda. So the number of pairs depends on this density lambda and the area of the entire grid. We obtain the wireless channel from ray tracing, and the second component in this effective channel is the DMA waveguide channel, which is a parametric function of the refractive index of the waveguide, the inter-element spacing of the slots, and the attenuation factor. So both of these together give us the effective DMA channel. Let's look at the performance metrics. For adhoc network, we use the conventional performance metrics like outage probability, transmission capacity, and energy efficiency. So the outage probability is defined as follows. We have outage probability as the probability when the SINR obtained after configuring the resonant frequency and the operating frequency is less than a certain threshold beta. So the beta is the outage probability threshold. Now it's difficult to get an exact expression for the outage probability, so we adopt Monte Carlo simulations. We iterate over different realizations of the entire adhoc network, and we average it out to get the approximate outage probability. Once we have the outage probability metric, then we compute the maximum density that can support an outage probability below a certain threshold. So epsilon is the threshold that we set in our simulations so that outage probability should be less than epsilon, and we want to find the optimal interfering density which can support this outage probability. Moving on, we have the transmission capacity metric, which is a function of this maximum density and threshold epsilon, and of course log to 1 plus beta, which is the capacity. So this metric shows the number of successful transmissions per unit area. And since we are investigating a frequency reconfigurable adhoc network, we are also interested in the transmission capacity per unit frequency. So we normalize this metric by the tuning bandwidth, which indicates the number of successful transmissions per unit area, per unit frequency. Finally, our goal is also to compare the adhoc network with DMAs to the conventional MMSE benchmark. And for that, we used energy efficiency metric, which is transmission capacity by the power consumption. In our simulation, we simulate the different performance metrics for varying number of DMA slots, tuning bandwidth, and transmit power. Let's look at the simulation of outage probability with respect to number of DMA slots. So in this figure, on the x-axis we are varying the density lambda, which is the density of the TXR expressed in the network, and on the y-axis we have the outage probability. So as we increase the density of the number of TXR expressed, obviously the outage probability will increase because there are more number of interferers. The interesting trend to observe here is that as we increase the number of slots on the DMA, we see that the outage probability reduces. So with just a single RF chain, and by changing the number of slots in the DMA, we are able to emulate the performance of fully digital receiver, which has the same trend as the number of antennas increase, the outage probability will reduce. So interesting, this DMA is also showing the same trend by just increasing the number of DMA slots. So as the number of DMA slots increases, the capability of the DMA to cancel the interference improves and the outage probability reduces. Going to the next simulation result, we vary the outage probability for different tuning bandwidths. So we vary the tuning bandwidth, which is the spectrum that is allocated to the entire network, from 1.6 GHz to 4 GHz. And as we increase this tuning bandwidth, we see that the outage probability reduces. So this is because there are two effects that are kicking in. The first effect is that as the DMA's tuning bandwidth increases, its angular coverage also increases, which means it can cancel out more number of interferers because of wider angular coverage. And the second effect is that as the tuning bandwidth increases, there are fewer number of interferers per receiver, which both of these effects help to reduce the outage probability. Finally, we show the plot of the normalized transmission capacity with respect to the tuning bandwidth. Here we see that as the tuning bandwidth increases, the normalized transmission capacity also increases, which means that a wider DMA tuning range supports a greater number of successful transmissions per unit area, per unit frequency. Finally, we compare the transmission capacity and the energy efficiency of the DMA with respect to the fully digital MMSC receiver. So the fully digital MMSC receiver has one RF chain per antenna, which means it has more power consumption and hence lower energy efficiency compared to a DMA. But the trade-off here is that the fully digital MMSC receiver is optimal in terms of the transmission capacity. So it has higher transmission capacity, but lower energy efficiency. So the DMA is a good sweet spot where we get reasonable transmission capacity with good energy efficiency. The key takeaways from the presentation are the DMA enables this new paradigm of frequency-reconfigurable adhoc network. DMAs with wider tuning range and greater number of slots increase the transmission capacity for adhoc networks. And we also showed the simulations where we compared DMA with the fully digital MMSC receiver and showed that DMAs are more energy efficient when operated at a wider tuning range. For future research, we are exploring some problems like how to obtain the necessary information for each TXR express, and also extend it to the case where the transmitter can have different transmit power constraints. Thank you, and I look forward to your questions and comments. Thank you.